wonder if some of these CEOs make statements like that, just market free advertising. Just after you say something like that, it's all over the news, it's everywhere.
Yeah. But I remember when he said that stuff. And to me, okay, freely admit I'm letting a little bit of my personal opinion come in through here. To me, it was not an anti-message. It was a pro-marriage, which is not an anti-message. So anyway, back to just a brief recap. We're talking about pipe networks. So systems that loop around on themselves. And here we have a basic pipe network with 2 loops. We've got a tank coming in, demands. We put all the demands at the nodes. The demands represent how much water is being used in that pipe network. We skeletonize it. In other words, rather than put a node everywhere there's a house or a business, we collect those into local points that represent then that this much water is coming out in this area. We define pipes, lengths, or number of loops, junctions, and fixed grade nodes. And we'll go through that fixed grade node in a little more detail. Is that as far as I got? I was thinking I had one more page of notes here, but I'm not.
You had the sign convention.
Oh, the sign convention, okay. Well, what did I do with that? Okay, well, just restart there and go from there. All right. So this already, you know, it's the sign convention then. So my sign convention was if I'm going with the flow, it's a negative, and against is a positive, and this is for the energy equation. Okay, and for continuity, we said in.
It's not showing up very well. It's very bright. There we go. Yeah.
Better? No?
There you go.
Good, okay. Thank you for pointing that out. Okay, in is positive and out is negative, and this is the continuity equation. All right. So now if I come back to the pipe network here, we've defined a direction around our loop. So maybe just put around here. So we assume loop direction. Oops. And for our main loops, be consistent. What do I mean by that? Well, you want to be the same direction. Okay, so you can note here in our little diagram that we did assume a clockwise rotation for both of these loops. Nothing magical about clockwise. I could have went counterclockwise, but if I do clockwise for one, I want to be clockwise for the other one. All right, and you'll see why here in just a minute. So now when I go ahead and write my equations for this, I want to keep that up there. It's not working too well. Okay, so the continuity equations. And you'll note that I've defined then the direction that I'm assuming the flow in each one of the pipes. Those are the arrows. That's purely assumed with some logic, knowing that the flow is only coming in at junction A. And so it has to be going out of junction A, but I can now write my continuity equation. Equation number 1 then is going to be, I need to call, I'm going to call this Q sub A right there. Okay, so I'm going to have Q sub A, and it's positive because it's going in, minus Q sub 1 minus Q sub 3 equals 0. That's my continuity equation at junction, at node A. So here's node A. So I've got the flow coming in, I've got flow 1 leaving and flow 3 leaving, and all that has to go to 0. Some of you kind of have some looks in your eyes. Is this making sense? We're doing okay? Okay.
Is that Q3? QA minus Q1 minus Q3?
Yes. Is that not showing up very well?
My eyes are not that good.
Okay, I'll write a little bigger. Or if you want, you can come down the front row here, Mark. So, okay. Those online, can you see that okay? Someone's gonna have to talk because I can't see the screen with your faces.
Yeah, just fine.
Okay, thank you. All right, so the second equation, then I'm gonna go to node B, and I'm gonna have Q sub 1 coming in, minus Q sub 2, minus Q sub 4 equals 0, and that is node B. And then I go to the third continuity equation, and I'm gonna have Q sub 2 coming in, Q sub 5 going out, and I have demand, the demand at C going out, and all that equals 0. Okay, D sub C represents then the demand. That's the water use at that node. How much are we pulling out of the system to supply homes and et cetera, factories, businesses, whatever. So that's the demand, and that's also then being taken out of the system. So I put that in my equation. Okay. Equation, and this now becomes node C. Come over to node D. Node D is simply going to be Q sub 3 minus Q sub 6 equals 0. No demand at that node. So the flow comes in, the flow goes out. Q sub 5, or my fifth equation, I'm going to have Q sub 4 plus Q sub 6 minus Q sub 7 minus the demand at node E equals 0. Q sub E, yes. Oh, I'm sorry, question?
No, I just got a little bit more.
Oh, at E, okay, so I need to write bigger. All right. Sixth equation then, I'm at F, so I'm gonna have Q sub 5 coming in, plus Q sub 7 coming in, and the demand at F equals 0. Okay. So there's all my continuity equations right there. Zach, doing okay? Okay. All right, so now that I've got my continuity equations, let's go ahead and write the energy equations. And remember that we said that for the energy equation, going back, the sum of the head losses equal to 0 around the loop. That was one of the criteria. We wanted the continuity equation to be equal to 0 at a junction. Now we're going to do energy at a loop. So if we start at any node, go all the way around our loop, then we're going to end back up at the same point, and so it has to be 0. Okay. So I'm going to slide this under here so we can now work on the energy equations. Okay, so I'm going to call the one on the left here loop 1, and the one on the right loop 2. So when I do loop 1, I'll start at node A. I'm going to go from node A to node B, and I'm going with the flow. So using the sign convention, it's going to be C. It's going to be minus C sub 1 times Q sub 1 squared, and that's going to take me to point B. I get to point B, And when I say I'm going with the flow, let me explain that. I follow the loop direction relative to the direction of the pipe. So since I'm following this loop and I'm going with the flow, I'm going to lose the hydraulic grade line. I'm going to lose the hydraulic grade line. I'm going to go up the hydraulic grade line. I'm going to go up the hydraulic grade line to get me back to A. Okay? So the direction on my energy equation is a function of the loop direction and the pipe direction. I compare those two. If they're going together, I'm walking down the hydraulic grade line. I'm losing energy. If they're going opposite of each other, I'm going up the hydraulic grade line. I'm gaining energy. So
Going together, they're positive?
if they're going together, they're negative
Oh, negative.
because I'm going in the direction of the flow, so I'm losing energy. Okay? The flow is losing friction loss as I go down the pipe. If I'm going against it, I'm walking back up the hydraulic grade line. So I get down here, the next one is pipe 4, so minus C sub 4 times Q sub 4 squared. And then I come over to pipe 6, following my loop, and this is going to be plus C sub 6 times Q sub 6 squared. And then I go to the next one, and I'm going up, so it's going to be plus C sub 3 times Q sub 3 squared, and all that equals 0.
Oh, Dr. Bruce,
Uh-huh.
sign convention?
Sign convention, once again, is right here. As far as the energy equation goes, if I'm going with the flow, if my loop and my pipe direction are together, it's a negative. If I'm going against it, it's a positive. Okay. All right. Energy equation number 2 then, my loop equation number 2. Oops. Come over here, I'm going to have minus C sub 2 times Q sub 2 squared because I'm going with the flow. Starting at node B, going to node C, and then from node C to node F, going with the flow once again, so minus C sub 5 times Q sub 5 squared. And then I come to 7. And you'll note that the loss of the flow rate is only inherent in the energy equation because the flow rates change. So I don't worry anything about the demands. They adjust the flow rates. The flow rates adjust the friction loss. It's all built into that, all right? So now I'm over here to pipe 7. I'm going against it, so plus C sub 7 times Q sub 7 squared. And then the last one then is I'm going against it, so plus C sub 4 times Q sub 4 squared equals 0.
Dr. Savage,
Mhm.
would it matter where you started on that loop as long as you went the right direction?
Yeah, it would not matter at all. You can start, yeah, and you could, in fact, you don't even have to go around the loop. You can jump, and say, oh, I want to start with the low numbers and go 1, 3, 4, 6, and that's perfectly fine. Yeah, it's going to work out all the same.
Follow the direction around.
Yeah, as long as you follow that direction, as long as you get the correct comparison between the loop direction and the pipe direction. Now, an interesting thing right here is you'll notice that pipe 4 is the common pipe between these two loops. And if you look at pipe 4, if I have a common pipe, they have to change direction because I have the same loop direction. So one's going to be going down, the other one's going to be going up. So that's a good check to always do, to check the common pipe, make sure that it's the same value for the C value because we're going to put this in a spreadsheet to solve it. Make sure it's the same value, it's just the opposite sign. Okay. So now when I look at this, I know that I have 7 unknowns, 7 pipes, 7 flow rates that I need to solve. And I have here 8 equations, 6 continuity equations, 2 energy equations. Right at the end on Monday, we said that one of the continuity equations is going to be redundant. And it doesn't matter which one, because I don't have any fixed grade nodes on my system. Once again, we haven't really covered fixed grade nodes in a lot of details, but look at this. logically, this should make sense to you. I know that I only have one flow coming into this system. Q sub A right there. So if I sum up the demand at C and the demand at F and the demand at E, I know that Q sub A has to equal DC plus DF plus DE. Has to. In order for just for continuity to work out. I can't be sending more water out of my network than water is coming in. For that very reason right there, that's why one of those equations is redundant. Okay? And it doesn't matter which equation you want to do. Bottom line is this: if I throw out any one of these equations, those flow rates are still going to appear in the other equations. For example, if I said I wanted to throw out equation number 4 as Q sub 3 and Q sub 6, well, Q sub 6 is right here, Q sub 3 is right there. So it's already built into these linear equations, so it doesn't matter. All right, so if you find yourself with one too many continuity equations, throw one out, it'll work out.
Does it have to be equation 4 to throw out?
Does it have to be what?
Does it have to be equation 4, the redundant equation?
You don't know which, they're all redundant. So it doesn't matter which one you throw out. Now, I wouldn't throw out the one, okay, I gotta be careful here, actually. The only one where that matters is equation number 1. Don't throw that one out. Because, and actually I think you could. And why you could is because if you throw that one out, you have all the demands in your system, and all the demands have to be equal what's coming into it. So yeah, equation 1's still redundant too. But it doesn't matter. The bottom line, it doesn't matter.
4 is probably the best one to throw out.
There is no best.
Oh,
Okay. Doesn't matter. They're all redundant.
okay.
One's not more redundant. I don't think that's a math term.
Oh,
So, okay. So now how do we solve this? Well, this is no different than a 3 reservoir problem, right? We now have 7 equations, 7 unknowns. 2 of the equations are nonlinear, but we know how to linearize them. Okay, so we're going to go ahead now and create a matrix for this. I'm going to put some little markers here up above. And let me start over. I didn't cram them together enough. So 1, 2, 3, 4, 5, 6, 7. That's 1 to 7. If you can't see that, that's all that is, 1 to 7. Okay. So I'm going to start off with my first equation. Let's assume that we want to throw out. Which one do you want to throw out? Anyone care? Should we throw? What's that? The second one? Second one's gone. All right. So we're going to start off, and when we do the matrix method, remember that any constants are taken over to the other side. So equation 1 then will actually be minus Q sub 1 minus Q sub, you guys can't see that, can you? Okay, minus Q sub 1 minus Q sub 3 equals Q sub A. Because Q sub A is now a known value. It's not an unknown value, right? So in my vector, or in my matrix now, I'm going to go ahead and write my first equation over here. And under Q sub 1, the coefficient of Q sub 1 is -1. The coefficient of Q sub 2, 0. Q sub 3, -1. 4 is 0, 0, 0, 0. And now I'm going to create my little matrix. I'm not going to close these brackets because I don't know how low they're going to go. But over here on my solution vector, now I have Q sub 1,
So,
Q sub 2, yes,
I have a question.
okay.
So do you assume the Q to be 1?
No, we're not assuming any flow rigs yet. I'm saying the coefficient, this is the coefficient matrix.
Okay, so like the -1, why is it -1?
Because what's the coefficient out in front of Q sub 1?
-1.
Negative 1.
Okay. I got it.
Okay?
It's just the coefficient.
Yeah, that's why we call it the coefficient matrix. We're going to grab the coefficients off of each of these terms, stick them into that matrix. Okay, and I've just put then my solution vector right here. All right, now I said, and now I have to have my B vector. And I made a mistake and no one called me out on it. When I rewrite my equation over here and move Q sub A over the other side, it becomes negative, right? So I'm going to put the value, Q sub A is known. I'm going to put the value of Q sub A right here then. So this is going to be a negative Q sub A. Okay. So now we threw out equation number 2. We can go to equation 3. Equation 3, there's no Q sub 1. Q sub 2 has a coefficient of 1. There's no Q sub 3 or 4. Q sub 5 has a coefficient of -1. No value for 6 or 7, but my B vector over here does have D sub C. When I take it to the other side, it becomes positive. So I get the demand at C over there.
Dr. Bruce,
Mhm.
I have a question. I don't get how you got the line, right? How did you get -QA and BC? Can you explain that again?
So if I take equation number 1 up here, Mark, and if Q sub A is known, if I take it over to the other side, it becomes this value right here.
Oh, okay.
And the same thing for equation 3. DC goes on the other side. The demand at C goes to the other side. Okay? All right, so now I go to the fourth equation, which now is turned into my third equation. Okay, so I'm going to have 0, 0, and then Q sub 3 is my first term. It has 1, and then nothing until Q sub 6, and it is a -1, and then nothing and no demand, so that is a 0 over there.
How come it's not BC?
How come it's not what?
BC.
Because there, if you go back to the original drawing, we don't have, DC is up above, and we're working on this equation right here.
Oh, okay. I thought we're doing equation 2. Oh, okay.
We're doing-
But
we're
on
doing-
2, right?
We're on 3, which is D now.
I got it.
So if I reorder this, this is 2, this is 3, this is 4, okay? So now we're going to go down to 4, and the first one that I have there is equation, or is 4. So 0, 0, 0, Q sub 4 is a positive 1, 0 for Q sub 5, Q sub 6 is a positive 1, Q sub 7 is a -1, and D sub E is over in my B vector. Then I go on to row 5. The first one there I have is Q sub 5, so 0, 0, 0, 0. And on the 5th column, I have a positive 1, 0 for 6, and a positive 1 for 7, and D sub F over in my B vector. And that now finishes my continuity equations, and now I can come down to my energy equations. And this is going to be row 6 and row 7. And the only thing I have to remember about these, just like we did 3 reservoir problem, is we want to linearize them. So we're going to let Q prime equal Q old. Okay. So put a little note down here. Q prime equals Q old. And so now when I come to the first position, I'm going to have negative C sub 1 times the absolute value of Q sub 1 prime. Okay. I have nothing for 3. I'm sorry, for 2. There's no term for pipe 2 in this equation. So now I come to 3, and 3 is going to be a positive C sub 3 times the absolute value of Q sub 3 prime.
Where did you get that?
I'm on equation number 6 right here. So I've got this term, and now I'm working on that term.
Oh,
Okay, I got to make sure that I get these in the right order. So if I took my solution vector, flipped it up to recreate my equations, they would all be in the right columns. Building the matrix, they got to be in the right column. Okay. Now I also have a value for Q sub 4, so it's going to be negative C sub 4 times the absolute value of Q sub 4 prime.
right,
And
after birth, it looks like Q prime equals Q, right? That's why it looks like the Q prime equals Q.
Q prime equals Q old.
Is that just something we assume all the time?
Yep. That's the notation that we're doing for this course. And I put these little dashed lines to represent that's the 4th column there. Okay. Now for the fifth flow rate, we have nothing going on there, so I'm going to put a 0. For the 6th flow rate, we have then a positive C sub 6 times the absolute value of Q sub 6 prime, and nothing for Q sub 7. I apologize, I'm starting to write small there again. And then keep going on to then the last equation. There is no C sub 1 there.
Does that equal 0 in the?
Oh, thank you, yes, and this is 0 over there in our B vector. So my last equation then, no Q sub 1, so I go to the 2nd column. And for the 2nd column, then I'm going to have a minus C sub 2 times the absolute value of Q sub 2 prime. No C sub 3. C sub 4 now is going to be a positive C sub 4 times the absolute value of Q sub 4 prime. And C sub 5 is going to be a negative C sub 5 times the absolute value Q sub 5 prime. No C sub 6. I'll put some little column marks there as well. And for the last one, it's going to be C sub 7 times the absolute value Q sub 7 prime. And that didn't work out too well there, but that is then the last of that. Everyone see that okay? C sub 7 times the absolute value of Q sub 7 prime. And that equals 0 as well. So now I have my A coefficient matrix. I have my solution metrics in my flow rates Q. And I have my B vector over here. And I can solve this exactly the same way that we did the 3 reservoir problem. Solve it for my Q values. It's good to take the average because this is a nonlinear system. So we slow it down a little bit by taking the average with our last guess. Stick that in and update our C values. Build a new coefficient matrix with the new C values. Solve it again. Keep doing that until it converges. Or rewrite all my equations in this form inside of Excel, all equal to 0, and plug it into the solver and solve that.
No, we just go way to go the first way or the second?
For this class,
Yeah.
both.
In our exam, probably the first one.
Well, for the homework, do both, because I could ask you either way in the exam. Okay.
So one
Now,
is the matrix
granted,
and one is
let's
the-
talk about the elephant in the room. You're going, well, does this mean we're gonna have our laptops with us in the exam? Well, no. What this means is that I'll probably ask you to solve the system, writing all the equations. And then if I want to see how well you're doing, I will give you a take-home portion for the exam. Because I obviously can't expect everyone to bring their laptop in and do this in the time frame of the exam. But I do expect you to be able to write the equations. And what I could do, in all fairness, is I could build a matrix and say, fill in the empty holes. Right? I can say, what are the parts that are missing in this matrix? There's a variety of things that I could do in an in-class exam to see if you understand this concept.
So this is regarding pipe network and all the matrices. What's the significance of this?
Yeah, we're solving this pipe network.
So once you get to this part, the rest is just plug it into your Excel program. And spits it out.
Yep. It's plug and chug.
So
In there.
Dr. Bruce, you might test us if we understand what this.
Oh yeah, not might.
Okay.
I could very well.
Because if you don't get it, then you won't know what
Right.
is put in there, and that's
Yes.
the point, it's a test.
Yes. And this is the methods that commercial codes use to solve pipe networks. Okay. Now there's also one where you balance the hydraulic grade line rather than doing the energy equation. So this is called the flow equations. There's another set called the head equations. It's two approaches to solving the same thing. I'm not going to go into that one. I think this is easier to understand. And most of the programs, I think, use this method.
So we don't have to use the circular method anymore?
The circular method is just an easier matrix method.
Okay.
And so, yes, I would say it would be good to know how to do that, because let's say that you did a simple project and your company didn't own the software, and you had maybe, I don't know, 15 pipes in this network. You were looking at some industrial process and it was loops. You're like, I can solve that. And, rather than spend the $5,000 to go buy the software, I'm just going to sit down and build my spreadsheet and crank it out. Now, would that happen? Yeah, probably not, but could it? Yes. But the more important thing is that you understand the mechanics of how the software program works. Because there are select times when we violate the principles and we get answers that are garbage. And so we need to know what's going on. I mean, we're just scratching the surface here. We still need to add minor losses. You already know how to add friction, how to do a change in friction, right? I mean, we just update the C coefficient every time. So we do loops within loops. We do one iteration. Take that, go over and find the Reynolds number. Take that and find then the new friction value. Bring that back, update the C value with the new C value and the new guess for Q, our Q old. We now create a new coefficient matrix. Take that coefficient matrix, solve it again. Solve for the new friction factor. You just loop it until it converges. Okay?
Is that what those programs do?
Yes,
It's all built into that.
it's all built in. They just run loops. They build these huge matrices. Now with Excel, I think you're limited to, I don't know how big you're limited on the matrix. The solver, you're limited to 121 variables. That's as big as the solver says. If you have more than 121 variables, no, I'm not going to do it. What's that? Yeah, it'd be 121 by 121. Okay. Now I don't know if there's a limit on matrices, and to be honest, I've never got close to the 121. All right, are we out of time? Oh, my phone died. Okay. All righty. So I will post the homework for you to work on a network. And I will extend the time for today's homework. I'll extend that, so if you're still working on it, you can still go back, try to get that to work, and make sure you submit that. All right, and otherwise, I'll see you on Friday. So have a great day, and hopefully you get some Chick-fil-A. Yeah.
Can I ask you a quick question?
Okay, let me copy this thing really fast. and then,
Team meeting in the car.
Hey, Zach, you know where to go to Africa or something?
Okay.
This is the homework problem that we were supposed to solve by hand.
Mhm.
It was really simple except for finding the friction factor because it wasn't given.
Oh, it wasn't given.
So
Oh, okay.
this equation was in the book, but it was never like in your notes. And like so I just used this equation and it like worked. And I talked to like some other people and that's what they did.
So the better equation is the Swami and Jane equation.
But that one you need the Reynolds number and I didn't have velocity. And so I didn't know how to solve it without because it gives me viscosity and the roughness, but it didn't give us like I didn't know how to find the Reynolds number or
Okay.
use the Moody diagram or anything.
So this particular equation only works if you're so far out in the Moody diagram. You know, the Moody diagram comes
Okay.
down and goes flat.
Uh-huh.
So if you're out there in that flat region, that equation works great. As
Okay.
soon as you get in the curved region, it fails.
I didn't know that.
Yeah.
So
And so there's enough flow in this pipe that you're out there in that region. So that's why that works. The more real way of doing this would be to guess a friction factor
okay.
and then solve it. And then once you get that flow, you know, you do the iterative process again. You know,
Okay.
once you get that, you update the friction factor, you solve it again until both the friction factor and the flow rate converge.
Okay, but how would I have? So I would have assumed a friction factor, plugged it in, and
Right.
solved these ones, and
Yeah.
then checked it.
Yeah.
Okay.
And did it give you a friction factor on these ones here?
No, it didn't give you any
Okay,
friction factor.
But it gave you
It gave you the roughness and
the roughness
viscosity.
and, okay, yeah. So on this one, you would have to use that iterative process to kind of go through that to refine it.
Okay.
But if it's way out there on the, you know, on the Moody diagram, that is a very good equation, but
Okay.
it only works for the, what we call the wholly rough section.
That makes sense. Also, are you gonna post the Excel solutions for the homework?
Yes.
Okay. I'm pretty sure I messed up on part of it, and I just couldn't find where I went wrong, so.
Well, maybe, I guess what I could do is I could post the solution, you know, so students could actually get work before they upload it. So maybe I'll do that.
I mean, I did upload like what I have,
Yeah.
but one
But
of
if you
them,
want to take a look at it and correct it and find the error,
cool,
because if you can find the error in this problem, then it'll make it easier when you get to pipe networks
yeah,
to understand the process.
that would be awesome, thank you.
Okay, all right.
Oh, no.
Hold on a
I
second.
think there's a class, I'm just gonna talk to you while you go to your office, but I won't go to your office, I'll talk to you along the way.
Okay.
It's just about, you know, how we're talking about the matrix, the circular and the solver.
Mhm.
So do we use that still in modern day practice now?
The solver in the matrix?
Yeah, and the
pipe
solver for
networks?
Excel, yeah, the solve type networks, or do we have more advanced software now?
We generally use software that is specifically for pipe networks.
That's a lot more advanced, but we have to understand where it's coming